All right, well, good afternoon, and welcome to the Electronic Warfare panel here at the Sea Air Space Symposium 2022. Thank you so much for being here. If we could go to the introductory slides that I had put up, and I'll kick us off here. Um, I thought to start our conversation, I just kind of set the stage here before I turn it over to our distinguished panelists. And noting that kind of in the grander scheme of human history and warfare, the electromagnetic spectrum is a relative newcomer in that grander scheme of things. Maxwell first introduced the equations for electromagnetism in 1860s, and by the end of that century, Marconi had built the first complete wireless telegraphy system or radio transmitter. Of course, with new technology comes new applications, such as military communications, but also new countermeasures. And so electronic warfare, or EW, found its start in the very early 1900s. Now, most sources cite the Russo-Japanese War as one of the first instances of EW in a military setting. The Japanese fleet was using radio to communicate with the Imperial Fleet headquarters, and one of the Russian warships wanted to transmit a stronger radio signal to try and distort the Japanese signal. The Russian admiral did not give permission to do so, and the resulting Battle of Tsushima did not go well for Russia. So over the last 120 years, technology has basically just increased our access to and our ability to manipulate the electromagnetic spectrum over greater distances and for more purposes. So today, we'll be discussing where electronic warfare is headed next. But before I turn the floor over to our panelists for their thoughts, I just want to give one quick sea story. So if we can go to the second slide. I recall my first warfighting exposure to the electromagnetic spectrum. I joined CNA in 2004, and I started in naval mine warfare. But about a year and a half later, I found myself in Iraq in the summer of 2006. We were working with the Joint Crew Composite Squadron and doing counter radio controlled IED work. That was probably the first time I ever saw a spectrum management chart, or maybe at least it was the first time I understood how important and how necessary something like spectrum management was. So that was just part of my introduction to the vast complexity and scope of EW. So with that, let's start hearing from our panelists, and let me introduce Captain Mckay. Our first speaker is Captain Duncan Mckay, who is the commanding officer of Naval Surface Warfare Center, Crane Division. Captain Mckay was commissioned as an ensign after completing Officer Candidate School, and his first assignment was with the USS Alexandria Fast Attack Submarine. After then going to the Deveron, he did a lateral transfer over to Engineering Duty Officer program, spent some time in the shipyards, a number of other assignments, including actually Portsmouth Naval Shipyard twice. But in 2020, just a couple years ago, he assumed command of the Naval Surface Warfare Center, Crane Division. Crane delivers innovative solutions and readiness to the nation and its warfighters through application of its technical capabilities. Captain Mckay, welcome, and over to you.
Sure. Good afternoon, everybody. So again, my name is Captain Duncan Mckay. I'm going to start off with a little bit of self-promotion here for Crane, just as kind of an intro to electromagnetic warfare. So next slide, please. So at Naval Surface Warfare Center Crane, located in Crane, Indiana, so we have 3 technical and 3 business departments. Our technical departments start off with global defense and deterrence. So that handles, we do trusted and assured microelectronics, mission engineering, strategic systems hardware, navigation and integration of combat systems. So we do a whole host of things there in global department. We have also expeditionary warfare department. We do a lot of maneuver surveillance and integration there. C3I integration, we have a lot of a heavy hand in that. Electro-optics, power and energy systems, and specialized munitions, which is actually some of Crane's founding function back in World War II. The next department, the third department, is actually our electromagnetic warfare department, known as Spectrum Department, locally, and it is exactly that. If you could go to the next slide, please. So our Spectrum Warfare Department is approximately 1,200 personnel, and they are devoted entirely to electromagnetic warfare. So that stems from that goes to everything through the specific technologies and specific implements And this is also multi-platform, multi-domain. So we have projects in the surface area, airborne, unmanned, cyber, et cetera. So we have the specific technologies themselves. We have people devoted to the modeling and sim that goes with it, to the doctrine, to developing fleet support, and training procedures, tactics, all that sort of stuff. So again, an entire department devoted to that. And it meshes quite well with our other two departments. So for example, electro-optics, which is, for a lot of folks know, that's just one part of the overall electromagnetic spectrum that David mentioned. And then also say our C3I integration. So that goes hand in hand with taking information that is developed and how do you use that? How do you make useful decisions out of that? So in addition to that inherent organic capacity and synergy that we have at Crane, just like our other sister warfare centers in NAVC, we are part of an overall larger economic ecosystem that's made up of not just our government institution and labs, but state and local government offices, and then also obviously our industry partners. We spend a lot of energy and effort and calories, as one of my department heads would say, on the specific technologies themselves, but we also work very closely with the higher level national labs and staffs to work specifically on the doctrine and policies that go into the larger electromagnetic warfare picture. So in some of the policy documents mentioned here, you hear that referred to as force level electromagnetic warfare, FLU, again, force level electromagnetic warfare. So that's distributed electromagnetic warfare, and that's spread across multiple platforms, multiple domains, multiple services, and it goes above and beyond just the individual technologies themselves. So the technologies and the specific technologies, their specific capabilities are necessary but not sufficient conditions to where the ideal state for force level electromagnetic warfare is. It's the combined effect of all of those and how we orchestrate them, how we maneuver, how we execute command and control for that larger picture. Next slide, please. So along those lines, so just a couple, I'll just spend a couple minutes on a few more specifics. So as far as force level electromagnetic warfare is concerned, you know, some thoughts to share. How can we add more dimensions to that effort? So how can we make it a more complex, but a more controlled picture? So that is definitely worth spending some energy and effort on, and we do that. So for example, unmanned platforms. So unmanned platforms in the traditional warfare domains, you know, we've had you know, multiple talks here. You can see lots of examples of that downstairs. So the electromagnetic warfare domain is no different. So how can we utilize unmanned platforms to add one more dimension of complexity to the problem and make it more of a problem for the opponent? But if we're able to control it, then that's more of an asset for us. So how can we increase the dimensional space for the warfare problem by using unmanned platforms? That's just kind of one example there of how to improve and where to spend energy for the force level problem. The next bullet, I'll just summarize as we talk about internally about this. One way to think about this is how do we teach ourselves new tricks with legacy platforms? So given an old tool, how do we sit there and scratch our heads and think about, hey, I can make this do some interesting things. How can I use this to my advantage? I shouldn't necessarily just automatically shelve it because it's overly simple, it's aged, it's currently understood by everyone, ourselves and perhaps our opponents. So what can I do with it to regain an advantage? And so that's what we typically mean by disruptive capabilities or non-traditional electromagnetic warfare is. Let's teach ourselves some new tricks with old hardware. And the last bullet, enabling technologies, actually I'm going to kind of run down and head right for the fourth one, mission engineering. So mission engineering is a very significant and important aspect of the overall electromagnetic warfare concept. So mission engineering helps us provide, or helps us give ourselves a lot of confidence in our training, our tactics, our procedures. It gives us confidence in the technologies themselves. We use it correctly. It then gives us confidence in when we knit all those together into an entire scenario. How does the scenario run? How does the command and control for the scenario run? That is all has a common theme in a robust mission engineering, modeling and sim capability and foundation. And then last on the list there, so AI/ML, so that's similar. That is not just, as Rand's probably going to talk about, AI/ML can be used in very specific circumstances to increase our advantage for a given scenario, a given platform, a given type of engagement. But artificial intelligence and machine learning is also extremely important for the preparation side. It's for getting us that force level EW, getting that right. There's multiple ways that we can use it just internally to the force to develop, I call it, as getting educated by my own folks, our test benches. So when we run, you heard, if you listen to the artificial intelligence panel from this morning that talked about data being the fuel for a lot of our AI machinery. So I have a fair amount of background in maintenance and ships and submarines, and so in my simplistic mind, I think of it as, how do we develop a really good test bench for our AI/ML, or rather our technologies? And the way we can build a really good test bench, and as some of you have any experience, a test bench is not, just any test bench is not the same as another. So you have good test benches that do a lot of things to verify your components and test your components, and then you can have really simplistic test benches that aren't really worth it. So how do we get world-class test benches to test our technologies and the tactics and the policies that go with them? AI/ML is needed for that as well, not just the executable operations of the technologies themselves. So there's lots of applications there. And so I'll stop there because I think that's a pretty good segue for Rand to talk about some of his stuff with on the AI/ML front.
Excellent, thanks, Captain Mckay. Our next speaker is Mr. Rand Hidalgo. He is currently the Director of Special Solutions Branch at Leidos, which specializes in the ongoing development of cognitive EW technology. Mr. Hidalgo previously served as the Senior Program Manager for both NAVAIR and DARPA Adaptive Radar Countermeasures programs, and led the development and transition of Leidos AI/ML-based solutions to address critical gaps in the airborne electronic warfare domain. Mr. Hidalgo has supported RDT&E and fielding of domestic and FMS EW systems across the defense industry over the last 16 years, including prior service as a U.S. Air Force officer with an R&D background in radar development, including Joint STARS, if you're familiar with that program, and the Airborne Instrumentation Systems Flight Test, the Test Pilot School. Mr. Hidalgo and his team at Leidos continue to perform groundbreaking research in the area of cognitive EW, which is what we're going to hear more about here, and are eager to explore transition partnerships through collaborative venues such as this year's Sea Airspace Conference. Thank you, Mr. Hidalgo, for being here, and over to you.
Thank you, David. Appreciate the opportunity to be here. Good afternoon, everybody. So representing Leidos today, my group works out of the Leidos Innovation Center. We're here in Arlington, and within that organization, we have a number of scientists and engineers and innovators that are essentially trying to develop new solutions as applied to the EW domain, right? So when it comes to the EW domain, it spans a lot of different areas, a lot of different use cases, whether it's communications, radar, whatever that may be. So what I'm going to talk about today is more of a specific use case when it comes to let's call it tactical airborne, right? Tactical airborne EW, specifically airborne EW self-protect. So since this is kind of a Navy venue and my background is aviation, I'm going to pick on the F-18 Super Hornet, right? So hopefully many of you are very familiar with that platform. It is the backbone of the Navy airborne fleet in terms of it being the workhorse. Primary mission, drop bombs on target, right? And Essentially, when you think about EW for that particular aircraft, it's not so much the forefront of that aircraft. It is something that the aircrew heavily relies on, okay? So an EW system within the Super Hornet does primarily two main things. Number one, provide SA, situational awareness. What does that mean? Well, if I'm aircrew, I need to understand what is in the environment. What are the threats out there that are potentially looking at me? Have I been detected? The next thing is, not only have I been detected, what is looking at me? Is this something that, is this an airborne emitter? Is this something on the ground, something on the surface? And then furthermore, as part of that situation awareness, is it escalating? Okay, is this all of a sudden an acquisition beam turning into a track beam, which is all of a sudden lethal to me? So that situation awareness component is a very important part of the EW systems that are applied to that aircraft. Now, once you cross that escalation threshold, now I have to count on my EW systems to put some sort of RF countermeasure out there, to do something to degrade the threat's ability to really shoot me down. Because again, my primary mission is not to jam emitters, it is to put bombs on target. And that is such an important mission for aircrew, and it really can dictate how sorties can actually be executed. So when it comes to looking at tactical aircraft, what we're doing at Leidos is essentially how do we put these systems postured in a way to handle things that you don't know about yet, okay? So when it comes to EW systems that are fielded today, a lot of how well these systems perform are based on what we call a priori knowledge, or the intelligence. Like, what do we know about threats, and how do we actually posture our systems and program our systems with the appropriate threat libraries in order for our EW systems to recognize the things that are out there and provide the RF countermeasures to counter those things. Now, I pose to you this question: what happens if you're in an environment against a threat that you don't know about? What happens if there is an emitter that's out there that is transitioning to something that is beyond your threat library? And the real issue there is you end up with a situation where your intelligence may not necessarily keep up with the pace of which your adversaries are actually developing these threat radars. So that being said, the transition to AI ML is certainly something that we need to start thinking about. Within industry, we're barely scratching the surface when it comes to applying AI ML into the RF domain. There's a term here that David mentioned called cognitive EW. And I've been working this type of technology since 2012, and that didn't exist. But during the time of prototyping algorithms and understanding how they work, that term kind of stuck, right? And it's really kind of the spearhead for where EW systems need to be going. And I'm not just talking about EW systems that are in development today that are going to be fielded with next generation aircraft. I'm talking about EW systems that are actually in the field today. What can we do to ensure that they are postured for things that you don't know about? So what happens, right, a particular use case when you are in using an EW system that is heavily reliant on intel? A lot of times if you're going up against advanced radars that you haven't seen before, complex threats, your situation awareness and your EA may degrade, right? So what cognitive EW solutions do is essentially change, not necessarily change that behavior, but supplement that expert knowledge in a way that allows the system to begin to understand the RF spectrum, okay? So a key thing to understand here, cognitive EW is essentially mission applied. In other words, when I talk about tactical EW systems is intended to protect the aircraft. Therefore, a cognitive EW solution doesn't necessarily need to learn everything in the environment. What's most important is the system learns what's trying to shoot you down, right? So, by doing that, you can kind of, tailor your solution for that particular mission to not only understand the environment, but also interact with it, right? So for those of you with an AI ML background, one of the key things to success is to kind of understand, I'm doing something, what is my adversary doing? So if you take a step back at what I just described, it's essentially an agent interacting with other agents in the environment. And applying that to the RF spectrum is certainly something that can fill the gap when it comes to going up against adversaries that have evolved beyond what your intel currently dictates. So that being said, it's also important to note that these types of solutions don't necessarily require a lot of hardware updates, okay? So when it comes to trying to update and provide some sort of upgraded capability to EW systems today, you can get away with some major capability gains through incremental software updates, right? And utilizing, you know, the digital and analog hardware that's already there, what you're essentially modifying is not so much how you do the signal processing, it's the decision making behind what you do with the signals that come in, and how to adapt, you know, your EA techniques, and to constantly put the radar operators on edge, because you are no longer just being static when it comes to EA, you are actually interacting with these adversaries. Okay. Finally, you know, when I say that these things are easy to upgrade, there are a lot of barriers in getting AI ML technology out the door. Number one is trust. Okay, so when it comes to aircrew, and I've you know, worked with tons of aircrew throughout the years, they are trained to the teeth to do what they need to do in the aircraft. But however, when all of a sudden we're talking about, hey, now your EW system's smart, it's going to be doing something. How do you incur that trust? You know, how does aircrew actually believe that it's doing what it needs to do? And because of that, within industry and across DoD, I believe there needs to be a lot of investment in the test and evaluation infrastructure for this new technology. So because of the fact that the way we do test and evaluation today is very much focused on how EW systems used to be designed, okay, with respect to leveraging threat libraries, MDFs, you know, a priori knowledge. A lot of times back when I was working earlier EW systems, I turn on a signal generator, throw that, you know, RF right in front of my digital receiver, and if all of a sudden within my scope I'm seeing, you know, the icon, and I see whiskers on the icon that indicates RF jamming is coming out, I look at a spectrum analyzer, I see the waveform, my job is done, right? When it comes to an engineer just checking out my system. Cognitive EW systems are a lot different, okay? There's going to be that closed loop back and forth because of the fact that cognitive systems are actively looking for vulnerabilities, and test infrastructure needs to adapt to ensure that that is in place in order to assess how effective these things are working. So again, thanks for allowing me to be here to share some of this. I think this is important technology that you know, industry needs to lean in on, and you know, the value that this can provide to all of the services, not when it comes to not only aircraft survivability, but all the, you know, all across the EW domain is pretty impressive.
All right, well, thank you very much. So given the things that we've talked about, I kind of want to start our discussion here first with noting that what you're both describing is not EW next, but there's sort of a next step of where EW is and where it's going. So let's start with that sort of comparison of kind of what you're describing, where you're focusing, and what's come before. So Captain Mckay, some thoughts about how you think about force level EW compared to traditional EW.
Sure. And I think it gets back to, we were talking before the panel started about how we've seen things progress. Mm-hmm. So, you know, you can think of in earlier phases, or even in some phases today, I mentioned before, it's platform specific, engagement specific, technology specific, scenario specific. It's the one tool, one situation. This is the size hex wrench that fits on this size bolt. You use it, it works very well. And so it's kind of a single application, and in some thoughts it's used for opening a door. Mm-hmm. It's used mm-hmm. for providing access for some other technology, some other platform to deliver a separate effect. I would say where we're going is it's no longer just opening the door, but we're using electromagnetic warfare concepts, technologies, platforms to go through the door. Mm-hmm. So to be more of a true arrow in the quiver of the combatant commander. And so that's a little bit, not being an electromagnetic warfare expert, but I can certainly see how that might be a paradigm shift from years of the past about that's, you know, more of more, and also just the concept of, hey, we need to get, so you heard, if you were at the breakfast this morning and listened to the 3 and 4 stars talk, but you heard about the discussion about, hey, at the fleet and the COCOM level, we need to operate as a joint force every day. So it is demanded that the components operate, the individual services operate as a joint force every day. So apply that same concept to electromagnetic warfare, and that brings in a different picture than the single tool, or rather, single tool, single application, that now gets woven into a whole, whole arrangement of similar operations going on. And so it's no longer just we use the one tool and we're done, but it's fitted in and networked in with all sorts of other similar electromagnetic warfare engagements, not just the kinetic stuff, but all the electromagnetic stuff. It's all knitted in. So that's again something worth investing calories in.
All right, thank you. And Ran, over to you, right? Your cognitive EW, you touched a little bit on how it's different than what's come before in the sense of trust. And what other sort of factors play into that make it different from kind of how we've done EW in the past?
Sure. So, when you say EW in the past, when it comes to self-protect EW, it's the same of how you're doing it today, right? A lot of it is based on investing heavily on the intelligence that you know about the threats that are out there. And your EW system is only as good as the intel that's baked in it. Because once you deviate from that intelligence and you are actually picking up signals that you've never seen before, then hopefully you've got an EW system that could gracefully degrade and still provide some sort of response. However, when it comes to moving more towards AI ML-based solutions, you are now able to explore that RF environment a little bit deeper, right? And I'm not implying that you essentially move away completely from that a priori knowledge. In fact, you still need to use that to bootstrap your EW systems going into the fight. Therefore, you're not trying to learn everything from scratch. The way that AI ML can be a force multiplier is, I'm going to throw three terms out there, and again, think of the Super Hornet with these terms: sense, adapt, and learn. Right. So when you think about the Super Hornet, those aren't the first 3 things you think about, right? But when it comes to the survivability of that platform, those three terms and functions essentially allow the system to characterize the RF environment and to really understand, of the things that are out there, what can shoot me down. But most importantly, independent of pilot action, that Super Hornet EW system has a finite number of electronic attack resources. So this becomes a resource management game, right, when it's all said and done. Without that AI/ML component, I could essentially underallocate or incorrectly apply my electronic attack resources to things that aren't really the threat, right? So when it comes to where things need to go, allowing that AI/ML component within the EW system gives a little bit more autonomous flexibility in how these things operate, and essentially assigns those resources appropriately. And one more key thing there, the concept of learning, right? Again, not your typical F-18 Super Hornet thing, but if you can imagine an AI/ML system that is interacting with the environment, and not only are they identifying from a situation awareness perspective what the threats are, or how threatening things are, or whether or not this is something that's ready to shoot me down, but you can also imagine a scenario where you are keeping tabs as to what type of electronic attack, right, is being applied. So when it comes to learning, and that's just one aircraft, right, and rarely do you see one aircraft go into a fight, you are with numerous aircraft. So therefore, you've got a lot of different contextual information across the aircraft that are in the fight that could potentially bring that information to the intelligence community to help truly understand and characterize that threat.
Yeah, the idea of resource allocation problem reminds me of that crew system that I mentioned in my opening comments when I was in Iraq and we were doing the counter radio-controlled IED. It was very much an intel-driven system. You had to really know what the threat frequencies were out there, and because the system really had limited resources that it could apply, right. And so you really needed to focus it first. And if you focused it wrong, that was a problem, obviously. Um, I think I want to save some time to come back to this AI/ML question, but it's a little bit of a rabbit hole, so I'm going to save it for last if we have time. I want to take a quick step back and kind of look at electromagnetic spectrum operations as a whole. And Cap Mckay, again, it's sort of from this force level EW standpoint, thoughts on what critical factors are that allow us to be successful in operations in the EMS.
Yeah, so I'm going to try and on the fly here, a couple things happen that I'm going to try and put together here. So number one, your slide in the beginning about the actual spectrum management plan there, and then Rand's discussion about the scenario where keeping the OP4 radar operator on edge. So one of the visions and places, again, I think is worthwhile that we spend some energy on is how do we get to a place in managing the force level operation where we are comfortable, confident, and very able to outpace and outmaneuver OP4. And doing that with, so how can we update our spectrum management plan in a faster and faster and faster fashion with more agility so that we are keeping the OP4 radar operators completely on their heels. So again, how can we get ourselves to a point where we can outmaneuver and outpace? So, what can we use to get there? So there's lots of things, certainly everything, I'll harp back on the test bench thing and how we need to, use, or at least impress upon the test bench concept with AI/ML. The more we're able to test in the backfield, before the operation, we know we'll get a sharper tool out there when it comes time that we need to use it. Another thing, just concept-wise, that we've talked about before internally is, again, something worth thinking about and getting to is, as a whole, how do we get out of a ammunition-limited thought process with certainly lots of things, but in particular with electromagnetic warfare. So what's preventing us from never running out of Winchester rounds, as we've said before around our internal conference rooms? How do we make sure the magazine never goes dry with electromagnetic warfare? And taken to kind of a fuller extent, for the kind of shipboard fundamental concept is, how can I really make full use of that ship service turbine generator on board the ship or the submarine or some other platform? So kind of thinking on that terms of making that sort of connection and how that can fit in, repeat that, as Rand said, you're never going to go out just with aircraft, you're never going to go out with one aircraft. So the force level concept is, well, we're never going to go out with one ship, we're never going to go out with one unmanned vehicle, we're never going to go out with one satellite, it's how do we what do we want the vision to be with netting all those together, and then how do we use the technology to get us there? So it's already out there, it's just us putting the effort forth to try and use it. So we were talking before earlier, software-defined radios. I sit in a STEM, I go to STEM briefs periodically where I am in Crane, Indiana, and I've got high schoolers talking about what they're doing with software-defined radios. We've got UA or unmanned vehicles all over the place. So how do we start integrating those? And AI/ML I've mentioned, so I think it's useful in some specific, more tactical applications, but back to the test bench, we've got multiple uses for it to hone our own technologies before we even begin to consider employing them. So lots of things we can do with just some of the basic technology thrust areas that we've got on hand right now. We can certainly use those. We just got to spend the energy to think about it, talk about it, communicate with ourselves, and make some decisions on where to go.
Now, a common theme that I think you both kind of touched upon is this idea of rapid development and fielding. And I think we've all witnessed, perhaps in the last decade, the Department of Defense struggling with this idea of how to do that in general. We've seen the birth of a lot of rapid capability types of organizations that are looking to kind of short circuit fielding and whatnot. So Rand, any thoughts on how the military and industry can work together to, there's a general sense that we need to be more rapidly developing and fielding. Any thoughts on how we do that?
Sure, sure. So, you know, my background has been in test, both in the Air Force and the industry. And to pull on the captain's thread here on test and evaluation, that can very much slow you down if you don't do it right. So within the context of AI ML technologies, you want to expose that technology to as many scenarios as possible, right? So one of the key things that could likely help improve feeling this quicker is the investment in automation, right? To ensure that even at the algorithm level, when you're writing an algorithm in MATLAB, that you are investing in the appropriate, let's just say NRE to develop the model for which that algorithm will reside on. You know, in the case of an EW system, you could essentially build a model of an EW system host that mimics the same interfaces that you would expect to see if you were integrated in that system, and allow your algorithms to be able to operate in as realistic EW environment as possible. And when I say automation, that's not just one test, that is throughout the week, right? Or when I go home on a Friday night, I'm going to kick it off, and then on Monday morning, I'm going to see my metrics and see whether or not things got better. Now, by doing that, there's going to be a point where that software has to get on a bench, and I have to go to the lab and test that out. If I did things right, I could essentially posture my hardware-in-the-loop test bench to mimic the same, let's just say, threat environment. Right, so we call it vertical testability. It's essentially applying the same type of RF signals that are simulated within modeling and simulation, and use those same models in hardware in the loop. Therefore, I can predict how well my algorithms are going to perform by the time I get to the bench. Now, the hard part's when you get over the air, right? So we don't necessarily always have access to the most advanced threat radars to test against in our ranges. Therefore, there has to be some sort of, you know, we have to lean forward in terms of understanding when I'm doing open air testing, how do I actually take the same stimuli that I started with in modeling, hardware in the loop lab, and apply that in the over air in the environment? Because what you're looking for are essentially the problems that are going to kick it back down, because that's what slows things down, right? So I've been in industry for 16 years doing flight test, and a number of times there were problems that I would never see until I'm actually in flight. And I'm actually, finding, software starts to reset for no reason. Well, why is that? Well, we got to figure that out. Was it the stimuli? Was it the, was it the way the aircraft was postured, or the mission computer, whatever that may be? You're trying to minimize, those situations where you have to kick things back to the vendor, right, in order to actually resolve. When it also comes to feeling this stuff quickly, it's also important to note that a lot of AI ML innovation is not going to happen with the vendors that are building your EW systems today. They are going to happen by, companies that do software, right? The best technology when it comes to AI ML aren't necessarily the iPhone itself. It is the apps that reside in the iPhone. You can think about EW in that same manner. When it comes to this technology, allowing third-party developers open access to existing systems and future systems is really going to change the game, right, in terms of how EW systems can behave. And that is a challenge, right, because there are a lot of the OEMs and the big vendors that build EW systems today don't necessarily like to expose their interfaces to third party. We get it, it's a business, but I think there needs to be some sort of concerted effort between the services, the government, and industry to allow other players to play.
All right, we just have a few minutes left, so I want to kind of pull the thread on the one rabbit hole that I mentioned, and you sort of just alluded to it. So before I do, another sea story that sort of sets the stage for this. My first field assignment was down in Texas in Corpus Christi at the Mine Warfare Command when it was located there. And the big topic at the time there was threat against US ports, right? So we were very worried about a homeland defense scenario where some crazy person might try to drop something in a port and shut it down. But it was a big issue from a defense standpoint because sailors are trained to recognize very set mind shapes when it comes to threats, right? The mark, whatever, pick a number, and this is what it looks like, and on a sonar return and all that. And so this question came up of how do you recognize something that you haven't seen before? And again, that idea of the intel picture coming in very importantly to at least give the indication, is it a refrigerator? Is it a 55-gallon drum? What should I even be thinking about looking for when I see a return on my sonar? And now, so tie that back into what you were talking about earlier with your systems. How do you train a system to recognize a threat that it hasn't seen before? And what I kind of want to get your thoughts on is, I think a common issue we see with a lot of machine learning stuff is being more worried about ensuring that the training database that we're learning off of, or the algorithm is learning off of, is representative of the expected operational space or the threat space. That by definition is not something you have not seen before. So how do you balance that where typically the approach is to train on known threats when suddenly now you have to be worried about something you haven't seen before? What allows to kind of bridge to that issue?
So one key thing to note is training AI ML systems is very difficult in the RF domain. It is. You just don't necessarily have access to truth, right? And that's a key component for the success of these algorithms. But the flip side to that is, moving away from an expert-defined systems where I use intelligence to identify that type of waveform is lethal. You cannot deviate away from the physics of a waveform, right? There are specific radar waveforms because of the fact that I am seeing this type of characteristics, parametric characteristics, that imply that I'm being looked at, right? And as I stated, applying AI/ML to the EW domain is very mission specific. In the case that I just described to you, I'm not trying to identify that thing that's looking at me. I am trying to tell the pilot, it's looking at me, do something about it. Whether or not it is something that I really want to characterize and try to bring that back home for intelligence to further scrutinize, that's not my mission here, right? So you can essentially posture your algorithms to really focus on the things that matter most. Again, when it comes to aircrew and the F-18, situation awareness and being able to jam.
All right, so we just have a couple of minutes left at this point. Any final thoughts before we wrap up here?
Thank you for having us.
All right. Well, we really appreciate the time. It was great to hear about the force level EW and the cognitive EW issues. Please join me in thanking our guests for this discussion.